Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This lecture is on other time series methods. And this lesson, our overview, the methods, the time series analysis methods we've learned in this course so far. And I will overview also other more advanced methods, which I will briefly introduce in this lecture. Let's return once more to the definition of a time series. A time series is a sequence or collection of random variables with some similarity in terms of the probability distribution called a stochastic process. For a time series, the sequence of random variables is indexed by time. Usually, no notational distinction is made between these random variables and their realized values. It is important, nevertheless, to bear the distinction in mind. In this course, we differentiated between modeling the conditional mean versus the conditional variance for univariate models and between univariate and multivariate time series modeling. The three classes of time series models we studied in detail are the ARMA model for modeling the conditional mean of univariate time series, the GARCH model for modeling the conditional variance of univariate time series, and the VAR model for multivariate time series. In this lesson, I'll overview these models along with other model approaches for time series. I will provide more details on each of the other models in the lessons of this lecture. Let's return now to the ARMA model. A time series is an ARMA process if it is stationary, and for every t, it is modeled as on a slide. It consists of two parts. The first part is the so-called AR or auto-regressive part of the model. The AR part of the model models the relationship between xt and past or lagged observations xt-1, xt-2 up to xt-p, where p is called the autoregressive order of the model. The second part of the model is the so-called MA or moving average. Using the MA part of the model, we can model that the time series at time t is not only affected by the shock at time t, but also the shocks that have taken place before time t. The moving average is a linear combination of white noise. In this formulation, Q is called the MA order of the model. An ARMA model can include both or just one of the two components. It can simply be an AR process or an MA process. We have learned that we can extend this model for non-stationary time series through a differencing or integration of the time series where the model is called a RIMA. In principle, this will account for the trend in the time series. Another extension is the seasonal ARMA, which accounts for potential seasonality in the time series. Altogether, the general model is the seasonal ARIMA. All the time series models provided in this course are models in the time domain. That is, they directly model the time-varying random variables. Alternatively, we can decompose a time series using the so-called spectral or Fourier decomposition and study the components of the decomposition AK and BK in the decomposition of XT on the slide. This type of analysis is called frequency domain modeling, and the time series analysis is called spectral analysis. The spectral decomposition is rooted in that well-behaved functions can be approximated over a finite interval to any degree of accuracy by a weighted combination of sine and cosine functions whose harmonically rising frequencies are integral multiples of a fundamental frequency. I will return to this analysis in the subsequent lessons in this lecture. The ARMA model and the spectral analysis primarily focus on modeling the conditional mean for univariate time series. Next, I'll review the GARCH model, which is the classic model for the conditional variance, and discuss another important application of modeling heteroscedasticity, that for high-frequency data. GARCH stands for Generalized Auto-Regressive Conditional Heteroscedasticity. The intuition behind this model is that it is a weighted average of past squared residuals, but it has declining weights which never go completely to zero. Hence, it models the impact of large variance for longer than the orders. The most widely used GARCH specification asserts that the best predictor of the variance in the next period is a weighted average of the long-run average variance, the variance predicted for this period, and the new information, which is the most recent squared residuals. Such an updating rule is a simple description of adaptive or learning behavior. For ease of understanding, I'm presenting first here the simple GARCH-11 model, which often is sufficient to model heteroscedasticity. The condition of variance sigma t squared is modeled using the lagged squared noise process zt-1 and includes the lagged relationship with past variability through sigma t-1 squared. More generally, a GARCH m and n for this that is of orders m and n is when the condition of variance depends linearly on the lagged squared noise process through zt-1 up to zt-m, but also through the past variability represented by sigma t-1 squared up to sigma t-n-1 squared. Thus, the interpretation of the two orders is as follows. M refers to how many auto-regressive lags or arch terms appear in the equation, while n refers to how many moving average lags are specified. The model was introduced by Borislev in 1986. By modeling heteroscedasticity requires different approaches when the data are observed at a much finer scale, for example, minute level or second level data. Such data are available or are seen in financial and medical fields. In this lecture, I will focus mainly on financial high-frequency data, although some of the modeling consideration introduced in this lecture will apply more generally. For financial data, the primary objective is to model the volatility at a lower data frequency, say the volatility within a day, from finer scale data, for example, minute level data. Another objective is to study market microstructure, related issues, for example, competition among related markets, strategic behavior of market participants, real-time market dynamics. I'll provide more background on this aspect in a different lesson in this lecture. The time series models as discussed so far primarily apply to univariate time series. However, it is often the case that we may be interested in modeling and explaining the interactions and co-movements among a group of time series variables. It is possible to improve the prediction of one time series by taking into account other factors. For example, hence time series analysis extends to multivariate time series modeling, allowing for modeling more complex relationships within and between time series. In this course, we learned about the extension of the error model for univariate modeling to the VAR model for multivariate time series. The vector autoregressive VAR model is one of the most successful, flexible, and easy to use models for the analysis of multivariate time series. It's a natural extension of the univariate autoregressive model to dynamic multivariate time series. The VAR model has proven to be especially useful for describing the dynamic behavior of economic and financial time series and for forecasting. The VAR model with lag P for an n-variate time series YT is defined similarly to the error model. YT depends on the YT-1, YT-P variables linearly. Now the coefficients are the matrices pi1 to pi p, which are n by n matrices of coefficients. The error term, epsilon, is assumed to be white noise with the covariance matrix sigma, covariance matrix sigma. A more general linear model for time series is the so-called state space model. A state space model for multivariate time series of dimensionality W, in this denoted here YT, depends linearly on an unobserved multivariate time series XT, also called hidden process, since it is unknown. YT is thus the linear transformation of XT plus a white noise process. The hidden process XT takes the form of a VAR of order 1 when XT is a multivariate time series, or an error process of order 1 when XT is univariate. Often this is also called a Markov process. We'll learn in a different lesson that the ARMA model is a particular case of this model. But because of this formulation, the state space model is more general. The models discussed so far are all linear models in the sense that they capture linear dependencies with respect to past history of the time series. A framework which allows estimation of non-parametric relationships and dynamics between time-varying processes is the so-called functional data analysis. We begin with multiple processes or so-called random functions which depend in our context on time, although they can depend on other designs, for example, space or frequency. We have n such random functions, or time series, each one observed at a set of time points, denoted here Tij, for the ith random function or process. The time points do not need to be the same across all the random functions. We can also have a fixed design when the time points are fixed in advance, but also we can have a random design when we have observations made at random time points, not known in advance. Last, unlike time series analysis, the time points can be observed sparsely or densely, depending on the experiment generating the random functions. The field for analyzing such data is the functional data analysis. I'll briefly point out common methodologies under this modeling framework in the last two lessons of this lecture. In summary, in this lesson, I overview the time series analysis methods that I introduced in this course, along with other methods that are more advanced and I will briefly introduce in this lecture. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm associate professor in the Stewart School of Industrial and System Engineering. This lecture is other time series methods. And in this lesson, I'll introduce the spectral decomposition of a time series, which is at the basis of spectral analysis of time series. Spectral analysis of a time series is one of the most widely used methods for data analysis in geophysics, oceanography, atmospheric science, astronomy, engineering, among many other fields. The basic idea is of transforming, or better said, describing a time series into high and low frequency signals, which can be interpreted in the context of the problem. In the nutshell, we compare the time series with sine and cosine functions at different frequencies. We can apply this idea to any time series, not necessarily a seasonal time series. Let's review the trigonometric cosine and sine functions. The first two plots on this slide show the cosine and sine functions. The next set of functions are again the cos and sine functions, but this time at a different frequency than those provided above. The difference is in the repetition of the seasonal pattern within a different range of time t. In the bottom plot, the number of time points is 128, and the repetition of the signal is twice. That is, we have two cycles or periods over the time period with 128 time points. What do the sines and cosine have to do with time series? In this last example, we can think of t to be time. To generalize, if we consider the functions cos and sine of 2 times pi times k over n times t, with t indicating time in this formulation, then we'll have a signal with k cycles or periods within n time points. K over n is called the frequency of the signal, since it is the frequency of the cyclical pattern. If k is small, we say that the time series have low frequency. If k is large, we say that the sine time series has a high frequency. In the cosine and sine signals provided so far, the amplitude of the signals is equal to 1, where the amplitude is the largest amplitude in those signals is the largest variation of the signal. That is, the range of the signal is from -1 to 1. If we change the range, if we want to change the range or the amplitude of the signal, we will just have to multiply the signal with some constant. And this is an example of a sine signal with frequency 7 over 128, or 7 cycles over 128 time points, with different amplitudes, one with amplitude 0.5 and the other with amplitude 1.5. In order to see the difference between the two signals, I plotted them on the same scale. We can add up sine and cosine signals at different amplitude with different amplitudes to obtain yet more complex signals. Such signals will look very different depending on the amplitudes A1 and A2. If you recall from the first lecture, we called from the first lecture of this course, we called this the harmonics decomposition used to model seasonality. Spectral analysis is thus the summation of lots of sines and cosines with different amplitudes, getting artificial time series that resemble actual time series. To be more specific, we can decompose a time series xt into a sum of harmonics at different frequencies k over n for k from 0 to big K. This decomposition is called Fourier or spectral decomposition. The spectral decomposition is rooted in the basic notation of Fourier analysis, which is used to approximate well-behaved functions over a finite interval to any degree of accuracy by a weighted combination of sine and cosine functions whose harmonically rising frequencies are integral multiples of a fundamental frequency. The difference across the decomposition of different time series is the coefficients AK and BK. Comparing time series means comparing the AK and BK coefficients in spectral analysis. These coefficients can be obtained directly using the formula on the slide. They are dependent on the time series XT. One way to describe or characterize a time series using its spectral decomposition is through its spectrum, which is defined as by the sum of squared coefficients for each frequency K. We can use a spectrum as follows. If frequency K over n is important, then Sk is large. Thus, the spectrum breaks the sample variance of a time series up into pieces, each of which is associated with a particular frequency. Spectral analysis is thus an analysis of variance technique. In summary, in this lesson, I introduced the spectral decomposition, which is at the basis of spectral analysis of time series. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This lecture is on other time series methods. In this lesson, I will continue with the introduction of spectral analysis for time series. In the previous lesson, I described the spectral analysis as the analysis of spectral coefficients from the Fourier or spectral decomposition of a time series. To be more specific, the spectral decomposition is a decomposition of a time series into a linear combination of sinusoids with random and uncorrelated coefficients AK and BK defined in a previous lesson. Spectral analysis is referred as analysis in the frequency domain, in contrast to the time domain approach we have considered so far. The frequency domain approach considers regression on sinusoids. The time domain approach considers regression on past values of the time series. In the spectral decomposition, the coefficients AK and BK are functions of the time series xt, which is a random process. Hence, the coefficients are random also. But most importantly, the coefficients can be shown that they are uncorrelated. Hence, the spectral decomposition takes correlated data in time and transforms it into uncorrelated spectral coefficients. Because we have only n observations, there are only n non-zero spectral coefficients. The autocovariance of the sum of two uncorrelated time series is the sum of their autocovariances. Thus, the autocovariance of a sum of random sinusoids is a sum of sinusoids with the corresponding frequencies as provided on the slide, where sigma k squared is the variance of the AK and BK spectral coefficients. If the sum of autocovariances across all legs is finite, we can define the spectral density as provided on the slide. Thus, the autocovariance can be expressed as a function of the spectral density, thus a one-to-one mapping between autocovariance and the spectral density functions. One essential property of the spectral density is that the autocovariance at 0, or the variance of xt, which is gamma 0, is attributed to the cyclical components of the process represented by the spectral density. Other properties of the spectral densities are that it's positive and symmetric function with periodicity equal to 1. To be more specific, we can derive the spectral density of a white noise as follows. Recall that the autocovariance of the white noise is sigma squared at lag 0 and 0 otherwise. We thus derive the spectral density as being sigma squared, thus constant across all frequencies. Each frequency in a spectrum contributes equally to the variance. In fact, this property is the origin of the name white noise. It is like white light, which is a uniform mixture of all frequencies in a visible spectrum. Another simple example which can help in understanding the concept of spectral density is the AR1 process. If xt is an AR1 process with AR coefficient phi, we learn that its autocovariance function depends on the coefficient phi as on the slide, with stationarity when the coefficient phi is not equal to 1. But we can also show that the spectral density depends on the coefficient phi as on the slide. We interpret the spectral density for the AR1 model as follows. If phi is positive, greater than 0, the spectrum is dominated by low frequency components, or smoothness in the time domain. If phi is negative, smaller than 0, the spectrum is dominated by high frequency components, which means roughness in the time domain. The spectral density of an AR1 with positive and negative phi coefficient is on the slide. We see that the spectral density decreases exponentially with the frequency when phi is positive, but it increases exponentially with the frequency when phi is negative. This is translated in smoother time series when phi is positive, as the simulated AR1 with phi equal to 0.9, versus the wigglier or rougher time series when phi is negative, as the simulated AR1 with phi equal to 0.9 on the slide. Thus, the spectral decomposition can describe such behaviors in time series. This lesson concludes the introduction of spectral analysis of time series. Thank you.